This is a discussion on the building blocks of the so-called cross-entropy laws. There are two varieties of it. One is the categorical cross-entropy laws, and the other one is the binary cross-entropy laws. As we have seen, the categorical cross-entropy laws is the loss function that we use when we have a multi-label classification scenario, and the binary cross-entropy laws is the loss function that we use when we have a binary classification scenario. Now, interestingly, the idea behind the cross-entropy laws is rooted in the field of information theory and probability. It's very important to understand how this laws comes to life. If you recall, the definition that we have used throughout of what the loss function, it was motivated like this, that loss is defined as the negative log of the predicted probability that a sample belongs to its correct class. So predicted probability that the loss for this sample, that is, so that the sample belongs to its correct class. So this is how we motivated the loss function, and it kind of makes sense. The motivation for this definition is that if the predicted probability is close to 1, so this is equal to, well, if the predicted probability is close to 1, so I'll write it as predicted prob that it belongs to the correct class. If it's close to 1, you have the negative log of 1. Log of 1 is 0, the loss is 0. If, on the other hand, the predicted probability that the sample belongs to its correct class is equal to 0, we have log of 0, which is minus infinity, and negative sign before makes it an infinite loss. And this is how we motivated. And this came to life because of the way the log function looks like. Right? So here is how the log function looks like. So you have the input and the output relationship like so. This is something we've already seen. So if this is the input axis, so this is the input, and the log of the input is going to look like this. So it's going to look like this. And precisely for log of 1, the input equal to 1, the log of the input is equal to 0, right? So and then the function grows very slowly past the input value of 1, and then it drops quickly to negative infinity. So this is something we've already seen. Now we are going to make use of the cross-entropy laws in understanding what is known as the generative adversarial network, or the GAN, and this laws also shows up in many other contexts. So the building blocks are as follows, right? So we're going to go through some seemingly disconnected steps, and then at the end you'll see that they all come together in a nice way to precisely understand what the cross-entropy loss is. So as I said, this is rooted in probability. So it's important that we recall certain ideas that we saw in APS about the expectation of a random variable, right? The expected value of a random variable. Now, there was a question on your APS exam that if you roll a die, what is the expected value that will show up? So the idea there is very simple. So what you do in practice is you would roll the die a million times, for example. You get, each time you roll, you get a value. Just sum them up, divide by a million. That is the simulation way of looking at what the expected value of a random variable is. So here the random variable is x, and it can take all possible values here, such as 1, 2, 3, 4, 5, 6, right? So what is the probability that the random variable x takes the value 1? The probability is 1/6, and it's the same for it to take the value 2, 3, etc. So the probabilities are exactly equal to 1/6. So it could also be different probabilities that the random variable takes these values, but in this case we assume it's a fair die. So the expected value of a random variable, by definition, once you have the set of possible values that the random variable takes, which in this case are 1, 2, 3, 4, 5, and 6, and the associated probabilities. The associated probabilities in this case are all equal to 1 over 6. Once you have these two sets of values, then the expected value we saw in APS last time can easily be written like this. It is simply the it's simply the weighted sum of the possible values that the random variable takes. So for example, it takes the value 1 with a probability 1 over 6, takes the value 2 with a probability 1 over 6, 3 with a probability 1 over 6, and so on, right? So 5 with a probability 1 over 6, and 6 with a probability 1 over 6. So in this case, it's just the sum from 1 through 6, like so, divided by 6. So this is 21 over 6, and the answer is 3.5. Right? So there is no value 3.5 that will show up when you roll a die, right? What that number 3.5 means is if you were to roll the die a large number of times and then average out the values that come out, you will see the average turns out to be 3.5. And this has a connection to simulation because we saw it last time that this value here, this 1 over 6 is what? This is the probability that the die rolls a 1, right? So this probability is precisely equal to, well, if you roll the die, for example, 10,000 times, right? Now you'll see that approximately 1/6 of those times it will show up, the number 1 is going to show up, right? So for example, this is like maybe like 1,600 times approximately, right? So and that precisely applies to the rest. And if you see that this is an average, right? So we are basically looking at the average of the rolls, and that is the simulation way of defining what the expected value of a random variable is. Good. So now that we know what the expected value of a random variable is, we're going to talk about the surprise associated with a random variable. The surprise. So surprise, you can think of it as a number just like the expected value. Surprise associated with a random variable. So I'm going to motivate this using a simple example to start with, right? Suppose I told you that there is a coin that is biased, and I also tell you that it's 99% of the times it's going to show up heads, right? Now, if you toss the coin and if you see a heads, well, you're not very surprised, but if you see a tail, you'll be very surprised. So is there a way to quantify the surprise associated with a random variable? It is possible to do that. So one way to define the surprise associated with a random variable showing up some value is to define surprise as this. So I'm going to use S of X here, like so. Surprise associated with the random variable, just like the expected value associated with the random variable, right? I'm going to say this is equal to 1 over P of X. What is P of X? P of X is the probability that the random variable takes the value X. So here I'm keeping X random, but then we can talk about the die, and then we can talk about the surprise associated with each roll that it's going to show up, right? So for example, what's the surprise associated with the roll showing up a 1, right? The surprise associated with the roll showing up 1 is simply equal to 1 over the probability that the roll is 1. Surprise associated with the roll showing up 1 is 1 over the probability that the random variable x takes a value 1, right? So this we know is equal to 6 because the probability that x is equal to 1 is equal to 1 over 6, right? So this probability is equal to 1 over 6, right? So now we can write this for all the remaining. So S of 2 is also going to be equal to 6. And you have the surprise associated with the die showing up 6 is also equal to 6. So, but then, this way of defining what the surprise is not very meaningful because let's say that just like the example I told you that there is a coin. Let's say that it can show up heads with probability 1 and it shows up tails with probability 0. This coin is heavily biased, right? So let's look at this example. There is a coin, x equals 1. Let's say 1 is heads with probability 1 and 0 is the encoding or the random variable's value when it shows up tail, and let's say that happens with probability 0, right? Now, let's talk about the surprise associated with the coin showing up 1. Are we surprised? Well, if we define surprise as the inverse of the probability, this is the probability that x is equal to 1, we get surprise is equal to 1. Well, we want surprise to be equal to 0, right? I mean, if this is a coin that always shows up heads, then the surprise associated with the coin showing up heads, it should be equal to 0. That's fine. We'll build towards that. How about the surprise associated with the coin showing up tails? So that'll be 1 divided by the probability that x is equal to 0, right? So somehow this is a little counterintuitive because the probability that x is equal to 0 is equal to 0. So we do have an infinite surprise. So this is kind of meaningful, right? So this is meaningful because the coin showing up, there is a coin that never shows up tails. If it shows up tails, what's your surprise? That's infinity. You have infinite surprise. But when the coin shows up heads, according to the definition of surprise, the surprise is equal to 1, not meaningful, right? So we would want this surprise to be equal to 0. So because if the coin shows up heads, your surprise should be equal to 0. So there's an easy way to do that. So we just have to tweak the definition of the surprise associated with the random variable. Tweak the definition of the surprise. So the way we're going to tweak is like so. We're going to define the surprise associated with a random variable. It's going to be very similar to what we had above, right? So the surprise associated with a random variable is not going to be 1 over the probability that the random variable takes that value. It's going to be the log. Now usually in the field of information theory, they use log to the base of 2. But for our discussion, you can assume this is log to the base of 10. So this is the definition of the surprise. Let's take the same example where we had this coin, right? So we're going to recalculate all these surprises. So I can just copy it till here. So let me put it here. Okay, let me just copy this again. All right, so I'm just going to put it back here because we're going to calculate the same thing with the new definition of what the surprise is, right? So this is what we have. So the new definition of the surprise is 1 over p of x, right? So I'm going to change this to 1 over log p of x. So let's just write this as the surprise associated with the coin showing up heads is equal to 1 over the logarithm of the probability that the coin shows up heads, which will be 1 over the log of 1. My bad. So it's log outside here. So let me just write it clearly. So the log is outside. So it's log of 1 over the probability that the coin shows up heads. So which will be log of 1 over 1, because the coin is always showing up heads, right? So log of 1 is equal to 0. So this is meaningful, right? So the surprise is 0 if the coin shows up heads. What about if the coin shows up tails? Well, we should have infinite surprise. Let's see if now what was not meaningful before has now become meaningful for the surprise associated with the coin showing up heads. How about the surprise associated with coin showing up tails? So let's write this down. It's going to be the log of 1 over the probability that the coin shows up tails, which will be the log of 1 over 0, which is the log of infinity. You can simply think of it as infinity again, right? So because I see the log is an increasing function, so even though it's slowly increasing, as the input becomes infinite, you can think of log of infinity as infinity, which means you have a big surprise, right? So this is also meaningful. So now we have come up with a meaningful definition of the surprise associated with a random variable. And that definition is this. The surprise associated with a random variable for each value is, for example, for it to take the value 1 is equal to the log of 1 divided by the probability that the random variable takes that value, right? But then there are many possible surprise values. What is the average surprise? So the average surprise associated with the random variable, the average surprise associated with the random variable, or the expected surprise, right? So what is the expected surprise associated with a random variable? So that is what? It is written like this. It's the expected surprise associated with a random variable x. Or I should actually put it as square brackets, like so. This is surprise associated with a random variable. What is the expected surprise? Now, why are we talking about the expected surprise? Because as we see here, for the coin toss example, there are two surprises, right? One associated with the value x equals 1. The other one is associated with the value x equals 0. So now if you want to get the expected surprise associated with the random variable, then what we are talking about is the expected value of what is s of x? Well, we just saw that s of x is log 1 over p of x. Log 1 over p of x. And this is precisely the entropy associated with the random variable, right? So this is what we call as the entropy. So what is this? This is the sum over all possible values that the random variable takes, right? And we're talking about the expected value of this quantity. So we're going to write down that quantity for each value of x, that is little x, multiplied by the corresponding probability that the random variable takes that value of x. So which is something we write it as p of x, right? So p little x, what I have written here. So I'll just write this in a slightly detailed way to start with. So this is the expected value of some function of this random variable. There is an x involved here. So you sum over all possible values that the random variable takes. Calculate that quantity. 1 over probability that x is equal to little x multiplied by the corresponding probability that the random variable takes that value, right? So the expected surprise or the average surprise associated with a random variable is called its entropy, right? So this quantity is called the entropy associated with the random variable x. This, or we simply say this is the entropy of the random variable x. Okay, so sometimes we write it like this. So the entropy associated with the random variable, so is the expected surprise, right? So I think you should clearly see now, if you're talking about entropy, what we are talking about is how much surprise can I expect if I were to realize that random variable, right? So what is the expected surprise if I were to realize that random variable? That is called the entropy associated with the random variable. It is a number. Bigger this number, the bigger your surprise when you realize that is the random variable takes a value and it is presented to you, right? So sometimes you will see this entropy written like so. So entropy is written as the sum over all possible values, P of x. Now this little P of x simply means the probability that the random variable capital X takes the value little x, right? Times the log of 1 over P of x. The P of x has the same meaning here again. And now we use the property of the logarithm that log of 1 over P of x is simply log of 1 minus log of P of x. And as we all know, log of P of log of 1 is equal to 0. This is equal to 0. So this is how you would usually see the definition of the entropy associated with a random variable, right? The sum over all possible values of x, there is a minus sign, the probability that the random variable takes the value x times the log of the probability that the random variable takes the value x. This is how you would typically see entropy defined, right? So let's actually look at an example and try to understand why the entropy is defined, or why it makes to define the entropy like this. So I'm going to copy this picture and put it here. Okay, so we have this picture where you have 3 boxes, and in each one of these boxes, you have 2 types of chickens, right? So let's call the boxes as box A. I'll use a different color here. So this is box A, this is box B, and this is box C, right? So now if I were to pick a chicken from box A, I'd be very surprised if it turns out to be blue, because blue is very rare in that box, and I'll not be very surprised if I picked up an orange chicken. So there is a large surprise associated with blue. There is a small surprise associated with the orange chicken. Similarly, in box B, if I picked up a chicken and it turned out to be orange, I'll be very surprised. On the contrary, if it turned out to be blue, I'll not be very surprised. Now, box C is the interesting one. If I picked a chicken randomly, and if it turned out to be blue or orange, my surprise is going to be the same, right? So how are we then going to calculate the surprise here? So for the purpose of surprise, in this calculation, I'll use log to the base 2, which is something that is typically done. But as I said, it doesn't matter which base you use. Just for simplicity, I'm going to use log to the base 2, right? So let's go ahead and calculate the surprise here. So what are the possible values of x here? So x can be, for example, so let me put it this way. So what are the possible values of x? X can be an orange chicken, or it can be a blue chicken, right? And what is the associated probability? Well, the probability that we pick an orange chicken is 6 over 7. the probability that we pick a blue chicken is 1 over 7, right? So what is the entropy associated with this random variable, right? So it's basically the probability that, so if you put in the definition, right? So what's the definition? The sum over all possible values that x can take, the probability that x takes the value times the log of the probability that x takes the value, right? So in other words, if I were to write this down, so it's going to be, or I can look at it this way. This definition is what we're going to look at, right? So first, it's going to be the probability that it's an orange chicken. So x takes the value orange. So you can give a numerical value for orange and blue, right? So for example, orange can be 1 and blue can be 0, right? So if that is, let's do it that way. Probably that'll be easier to relate to the values that you see there. So let's say that orange is equal to 1 and blue is equal to 0, right? So what is the entropy? So we're going to make use of this definition. First, it's a probability that x takes the value 1, that is, you get an orange chicken, times the log of 1 over the probability that you get an orange chicken, plus probability that x takes a value 0, that is a blue chicken, times the log of 1 over the probability that you get a blue chicken. So now what's the probability that you get an orange chicken? It's 6 over 7. So as I said, we're going to make use of log 2 as for simplicity. So P of 1 is 6 over 7 here, and P of 0, the probability that you pick a blue chicken, is 1 over 7 times the log of 1 over 7. So if you do the math, well, as you see here, there are two parts, right? So the surprise associated with picking a blue chicken is pretty high. So if you calculate this number, it will be pretty high, whereas the surprise associated with picking an orange chicken is not that high. So if you do the calculation, you will get the expected surprise, which is the entropy associated with this box, is equal to 0.59. So this is the expected surprise, right? So we just calculated what the entropy is associated with box A. Let's calculate the entropy associated with box B. So in this case, I'm going to write down the same thing. So 1 is going to be orange and 0 is going to be blue. But then in box B, the probability of picking an orange chicken is very small. It's 1 over 11. Whereas the probability of picking a blue chicken is pretty high. There are 10 out of 11 chickens that are blue. So let's calculate the entropy of box B, or the entropy associated with the random variable x. That tells us what the next random chicken is, right? What is the expected surprise in picking the next random chicken? Again, it's the probability of the random variable taking the value 1 times the log of 1 over the probability of the random variable taking the value 1. So same thing, P of 0, log of 1 over P of 0. If you put in the values, now P of 1, the probability that you take an orange chicken is 1 over 11. And again, I'm using log 2, 1 over 11. The probability of picking a blue chicken is 10 over 11 times log 2, 1 over 10 over 11. Now, in this case, you see that the surprise associated with picking an orange chicken is going to be high. This number is going to be high because it's very rare, whereas the surprise associated with picking a blue chicken is going to be low. Now, if you do the math, if you add them together, you'll see that the surprise is 0.44. Now, the third one is the most interesting scenario. So here again, x is equal to the value 1, which corresponds to picking an orange chicken. That probability is 7 over 14. So there are an equal number of orange and blue chickens here. And the probability that x the x equals 0, which corresponds to picking a blue chicken, that also has a probability 7 over 14. Now, what is the entropy here? So this is the probability of picking an orange chicken times the log of 1 over the probability of picking an orange chicken, which is the same as the probability that the random variable x takes the value 1, probability of picking a blue chicken, probability that the random variable x taking the value 0, times 1 over the probability of picking a blue chicken, which is the probability that the random variable x takes the value 0. So if you plug in the numbers, probability of 1 picking an orange chicken is 7 over 14. You have log 2 of 1 over 7 over 14. And here, probability of picking, this is 1 is an orange chicken, 0 is a blue chicken, is also 7 over 14 times log 2 of 1 over 7 over 14. Now, interestingly, you see that the surprises are the same because there is an equal number of orange and blue chickens. So this will be 7 over 14 times log 2. So 7 over 14, the reciprocal is just 2, log 2 of 2. This is 7 over 14 times log 2 of 2. As you all know, log 2 of 2 is just equal to 1. So this is equal to 1. This is equal to 1. So you have 7 over 14 plus 7 over 14. The entropy is equal to 1. The entropy is the maximum in this case because the surprise is equally distributed across the two possibilities, right? So, so that is the definition of the entropy associated with a random variable. Quick recap, the surprise associated with a random variable is defined as the expected, or for a particular value, it's the logarithm of 1 over the probability that the random variable takes that particular value, right? So this was the definition we started with. So the surprise associated with a random variable taking a particular value is log of 1 over the probability that the random variable takes that value. Let me just open this again. Okay, so now from the definition of the surprise, we went to the notion of an expected surprise. On an average, how much surprise can I expect the next time I realize that random variable? So in the chicken example, how much surprise on an average can I expect the next time I pick a chicken from the box? So this was the tweaked definition of what the surprise is. Okay, let's go here. Okay, so this is the tweak definition. This is the definition of surprise. This is the correct definition of surprise associated with the random variable taking a particular value. The average surprise or the expected surprise is what is known as the entropy, right? The expected surprise is the entropy. And that goes by this definition. So most of the times it's written like this. Entropy is shown as this last expression. Right, so that's what I just calculated here, right? So you see that the entropy is the largest when the surprise is equally distributed among the different possibilities that the random variable can correspond to, right? So why did we do all this? So because now we know what the entropy associated with the random variable is, right? So I'll just write this down here. Let me just close these again. Okay, so let's write down the entropy. All right, so the entropy associated with the random variable is this. I'm going to write down the formula again. So now you know what it means. The entropy associated with the random variable is the expected surprise. The surprise of the random variable is log of 1 over p of x. X is random, so this corresponds to all possible values. So we sum over all possible values of x. We have log of 1 over p of x times p of x here. Now this is generally written like so. This is what I want you to keep in mind. P of x log p of x. So this expression, the last expression, is how you typically see entropy defined. So now we know what entropy is. Now you probably are kind of wondering, this is where the notion of cross-entropy came into picture perhaps, right? Because the loss is called cross-entropy loss, right? So we know what an entropy is. What exactly is a cross-entropy, right? So in order to understand, we have to look at what is known as the Kullback-Leibler divergence. Now, this might sound a little heady, so sometimes also written as scale divergence, right? So this might sound a little heady, but this is a very important idea in machine learning, and this has a connection to the cross-entropy loss, right? So I'm going to motivate with an example again. Let's say that there is a particular coin, and you know that this coin generates heads and tails a particular way, right? So, for example, let's say that you have coin 1, right? And you know that the probability that coin 1 shows up heads, so the probability of this coin showing up heads, you know, is equal to P1. I'll use a lowercase. So this could be, for example, 0.5, right? So some value, right? So the probability that this coin shows up heads is equal to P1. The probability that the same coin shows up tails is equal to Q1. Let's say you know these numbers, right? So for example, for a fair coin, P1 is 0.5, Q1 is also is equal to 0.5, right? Now, what you do is you just toss the coin, right? And you observe a sequence. So you observe a sequence here. The sequence would be a bunch of heads and tails, right? So let's say it looks like this: heads, tails, heads, heads, tails, tails, heads, and it goes on, right? Now, what we want to do is this. Suppose there is another coin, right, that your friend comes up with. And your friend claims that the coin that you have has the same distribution as the coin that he or she has brought in, right? So in other words, your friend is claiming that if I generate this is your friend speaking, if I generate a sequence with my coin, it'll kind of match the sequence that your coin generated, right? So your friend is claiming this, that he or she is tossing their coin, they get a sequence, right? So, and they are claiming that my coin will generate a sequence that is very similar to yours, right? So the question here is, uh, how is it possible? How, can we quantify the ability of your friend's coin to generate the same sequence as what your coin generated, right? If the distributions, meaning the probabilities, are similar, then there is a high chance that the sequence that you generated can also be generated by your friend's coin, right? So let's say that your friend's coin has a probability of heads is equal to P2 and probability of tails is equal to Q2, right? So the question we are asking now is, how likely is it for your friend's coin to generate the same sequence? Okay, so it is the same sequence. So I'm just going to copy this. How likely is it for your friend's coin to generate the same sequence? Like so. So let's go ahead, calculate those probabilities. What's the probability that coin 1 generates that sequence, right? So what's the, one second. So what's the probability that coin 1 generates the sequence? Let me open it again. So the idea here is, if the distributions are similar, meaning if coin 2 has similar probabilities just like coin 1 of generating heads and tails, then the sequence that the coins will generate will also be identical. That means if I were to toss the second coin, I should get the same number of heads and tails, right? That's the idea. So what we're going to do is we're going to say, what's the probability of coin 1 generating the sequence? So what is that probability? We know how to calculate it. So first it's at heads. So heads and tails is Q1, and heads is again P1, and tails is Q1, and tails is Q1, and so on, right? So this is the probability that the coin 1 generates the sequence, right? So let's say that you toss the coin n times. So here you toss the coin n times, out of which we had nh number of heads and nt number of tails. So the question we are asking is, well, how likely is it for your friend's coin to also generate a similar sequence if you toss the coin n times? That is, you should get nh heads and nt tails, right? So similar distributions should generate similar sequences is the underlying idea. So here this is P1 multiplying how many times? nh times, because nh is the number of heads, and Q1 is multiplying nt times, because nt is the number of tails. So this is the probability of coin 1 generating the sequence. Now what's the probability of coin 2 generating that exact same sequence? What's the probability of coin 2 generating that exact same sequence? So it will be the same thing, except that I should replace P1 by P2, because P2 is the probability that your friend says the coin shows up heads, and Q2 is the probability that your friend says the coin shows up tails, right? Okay, now if the distributions are identical, then these two values should be the same, right? So your friend may not know what P1 and Q1 are, right? But if the distributions are identical, these two values, by these two values I mean this one and this one, these two probabilities should be the same, right? So what we write down is known as the likelihood function, right? So the likelihood function looks like this. What's the probability of generating the sequence given that it's coin 1 divided by the probability of generating the same sequence given that it's coin 2, generating the same sequence given that it's coin 2, right? So this is called a likelihood function, right? This is the likelihood. Now if these two coins have the same distribution, underlying distribution, this value will be equal to 1, right? So we just write down the expression like so. n1 to the h, and like so, p2 to the power nh, and q2 to the power nt, right? So now what we'll do is, since these values can get very small, right? We're going to normalize them. So this is called the likelihood. So we're going to normalize the likelihood by sort of taking the geometric average, so to the power of 1 over n. So you have the likelihood to the power of 1 over n. So this is called the normalized likelihood, right? Now, what we do after this is we take the log of all this. So it's the log of the normalized likelihood. The log of the normalized likelihood. Now this is what we define as the KL divergence between the distributions of the two coins. Now one thing you immediately see here is that if both coins have the same distribution, then this term inside the parentheses is equal to 1, right? So 1 to the power anything is 1, log of 1 is 0. There is no difference between the two coins. On the other hand, if the distribution of the second coin becomes very different from the distribution of the first coin, the numerator here will be different from the denominator there. The divergence will, or the value will be different from 0, right? So let's go ahead, expand this out. So this is the property of the logarithm, right? So the 1 over n will come sit on the front side. Then you have the log of the ratio of two things, which is simply the log of the numerator minus the log of the denominator, like so. And now we make use of the property of the logarithm again, that the product of the log of two things is the log of the first thing, log of p1 to the power nh, plus the log of the second thing, q1 to the power nt. And here we'll have log of p2 to the power nh, plus there's a minus again, log of q2 to the power nt. So we again make use of the property of the logarithm that the nh comes and sits on front. So now I can write this as nh over n log of p1 plus nt over n log of q1 minus nh over n log of p2 minus nt over n times log of q2. Now keep in mind what is that we have done here. There is a sequence that is generated by coin 1. We are asking the question that how likely is it for coin 2 to generate the same sequence? How do we calculate that? We calculate the likelihood ratio. So the numerator is the probability that coin 1 generates the sequence. The denominator is the probability that coin 2 generates the same sequence. This is the likelihood ratio. This will be equal to 1 if coin 1 and coin 2 have identical probabilities. That is, P1 is equal to P2, Q1 is equal to Q2 of generating heads and tails respectively. Now what we do here is we normalize the likelihood ratio and then take the logarithm. Why we take the logarithm? Because if the distributions for the coins are the same, log of 1 will be 0. This is what we define as the divergence between the two distributions, or you can think of it as the dissimilarity between the two coins. So this is what we end up with. But now there's something very interesting. What is this nh? What is this nh over n? It's the number of times heads showed up divided by the total number of times we tossed the coin. For large values of n, this is precisely the probability that the coin shows up heads, the original distribution that you know, right? You know the original distribution is the probability that the coin shows up heads is P1, the probability coin shows up tails is Q1. So the number of times heads showed up, what fraction of times heads showed up among the n times you tossed is P1. So you have P1 times log P1, And nt over n is the fraction of times tails showed up when you tossed your coin, your original coin. That'll be q1 times log q1. And similarly here it's p1 times log p2 minus q1 times log q2. Now observe that I'm just going to combine, so let me open it again. OneDrive is just crashing for some reason. So I'm just going to combine some of the terms here. So, and then we're going to get to what's known as the KL divergence between the two distributions. It is a single number that quantifies how different the two coins are. In other words, under the hood, how different are the distributions associated with the two coins? How different are the probabilities of the coin showing up heads and tails are different among them. This is what we have. So I just wrote down, so that went away. So this is P1 log P1. This is Q1 log Q1. This is P1 log P2 minus Q1 log, there's a Q2 here, Q2. So now I'm going to combine a few terms. So I'm going to combine this term with this term and this term with this term. Okay, so what we derive after this is there's a P1 that's a common factor, and log of P1 minus log of P2 is log of P1 over P2. And when I combine these two, Q1 is a common factor, and log of Q1 minus log of Q2 is log of Q1 over Q2, right? Now, interestingly, this is called the KL divergence between the two distributions. So when I say two distributions, you can think of it as the two coins and the corresponding probabilities associated with the two coins. The probabilities associated with the first coins are P1 and Q1. The probabilities associated with the second coin are P2 and Q2. How different are the two distributions? We write it like this sometimes. The KL divergence between two distributions P and Q is defined as, now it's kind of interesting to see what this is. This is defined as the expected value of the log of P of x over Q of x. So this might look a little confusing, but in just a second it would be meaningful. OneDrive is just crashing. Let me just pause this for a second. Okay, so the KL divergence between two distributions is defined as the expected value of the log of the likelihood ratio. So what is this? So this is simply this, that there is some random variable. I know that the true distribution is P. What do I mean by that? So for example, the probability that the coin shows up heads, I know is this value. The probability that the coin shows up tails, I know is this value. Somebody else comes and claims that I have a different distribution for that coin showing up heads and tails, just like the example I showed you about. So we want to calculate the expected value of the ratio of the log, or the ratio of the likelihoods with the log applied. So if P and Q are identical for all values of x that the random variable takes, P of x over Q of x is 1, log of 1 is 0. So the expected value of a whole bunch of zeros is equal to 0, right? There is no divergence between P and Q. The moment Q and P differ from each other, then we get a divergence. So this can be written as the summation over all possible values that the random variable x takes, right? What is the expected value of something that involves an x? The probability that the random variable x takes the value x according to the true distribution, which is what I have, times the log of the probability that the random variable takes a value x according to the true distribution divided by the probability that the random variable takes a value x according to your friend's distribution. Now this is what we sometimes write like so. The KL divergence between two distributions P and Q is the summation over all possible values of x, P of x log P of x. So P of little x is basically the probability that the random variable takes a value, a capital X takes a value little x, P of x divided by Q of x. Now what is Q of x? Well, it's the probability that the random variable takes the value little x, but according to your friend's distribution, right? So this is according to your friend's distribution. This is the same thing we saw earlier, right? You see, this is exactly the same thing. P1, Q1 are according to your distribution, the same P1, Q1. That's the same P and P that you see here. P2 and Q2 are according to your friend's distribution. That is the Q that you see there. So this is the KL divergence between two distributions. In other words, how different are the two distributions? If the distributions are the same, then across all possible values of x, P of x, which is the probability that x takes a value x according to the original distribution, should be equal to Q of x, which is x takes the value little x according to your friend's distribution. So if they are equal, log of 1 is 0, then the whole thing becomes 0. Even if there is one value of x for which the probability capital X, the random variable, takes that value of x is very different according to the original distribution from it taking the value little x according to your friend's distribution, there will be a difference between the two distributions, right? That's what the KL divergence is. Now it's most of the times written like this. How different are these two distributions? Well, we make use of the rule of logarithm. So you see here that you can write it as P of x times log P of x and then minus, so log of P of x over Q of x is log P of x minus log Q of x. You have P of x log Q of x, like so, log of Q of x. Okay, so, and now you see where the entropy comes into play, right? So this is the KL divergence. How different are these two distributions? I'm going to write it slightly differently, right? So I'm going to write this term first. So I'm going to write this term first. So it's going to be the summation over x. So I'm going to separate it out. You have minus P of x log Q of x. So think of it as the first term. I'll put it in a box. Okay. And then I'm going to add a minus sign, like so here. And then I'm going to write the first term again. So this is going to be x. So since there is no minus sign on front, I'm going to put a minus sign here, and you have P of x log P of x. And this is the second term, so which I'm going to box like so. So as you see, they're both the same, right? I mean, the one on top is the same as the one at the bottom. You get the same thing. Okay, so this is what we have. So now I'm sure you're able to recognize a few things here, right? What is this thing here on inside the pink box? You may want to just recap about what we said about the entropy associated with a random variable. So do you see that this is simply the entropy, the expected surprise associated with the random variable x? This is the entropy associated with the random variable x, or the underlying distribution. So what is the entropy? It is the expected surprise, right? So I'll put a double arrow. What is the expected surprise I can expect if I'm going to realize the random variable x? Given that I know its true distribution, remember P is the true distribution. Given that I know the true distribution, how much is my surprise? So I'm going to write this here. How much is my expected surprise given that I know the true distribution? Given that I know the true distribution. That's what I have written below. So it's like my surprise, the surprise associated with someone who knows the true distribution. What about this quantity here, right? Now this quantity is kind of interesting. This is simply the entropy associated with someone who thinks that the distribution is Q, right? You see, if they knew the original distribution, then this is the entropy. But they are thinking that Q is the distribution, and then they calculate the expected surprise. So this is simply the expected surprise. How much is the expected surprise for someone who thinks Q is the original distribution of the random variable x? Q is the true distribution. Q is not the true distribution, right? But they think Q is the true distribution. So they know, there's a particular function Q. For every input x, it gives the output. Then they calculate the surprise. So do you see here that this here is the expected value of, so this here is the expected surprise, which is log of not 1 over p of x, but 1 over q of x, because that person is thinking that the true distribution is q of x. How much is their surprise? And this here is how much is your surprise, because you know what the true distribution is, right? So what is the difference between our surprises? So the difference between our surprises. So let me put it here. The difference between the surprises of someone who thinks Q is the original distribution and someone who knows that P is the original distribution. Now, obviously, if Q and P are the same, your friend's surprise is not going to be different from your surprise. So the divergence is going to be 0. But as soon as there is a difference between Q and P, then the surprise is going to build, right? So this is the KL divergence, right? So this is basically the sort of the difference in the surprises, so to speak, or how different are these two distributions P and Q. So I'll write it one more time. So it's written like this: the summation over all possible values of x, P of x log Q of x minus, or now I'll just put the plus, because minus is plus. I did that to show the difference between surprises way of interpreting it. And then you have plus x, P of x log P of x. Okay, so now this quantity is also called the cross entropy. This quantity is called the cross entropy between the true distribution P and the distribution that is trying to match it Q. So this is the cross entropy between P and Q. So you see that the KL divergence is simply the difference between the cross entropy between P and Q and the entropy of the distribution P. In other words, it's the difference between the surprises, right? So long story short is, yeah, this is the KL divergence. So this involves the entropy, right? So in this boxed expression, what is the entropy? So we all know that this is the cross entropy. That's where the cross entropy loss comes into play, right? So here is the cross entropy, and this is the entropy associated with the distribution P. So now, where does the cross entropy loss comes into play? Now remember the sort of sequence that we talked about. We started with the expected value of a random variable, right? So this is just a quick roadmap recap. So we talked about the expected value of a random variable, expected value of a random variable. And from there, we went to the expected, and then we talked about the surprise of a random variable. And from there, we talked about the expected surprise associated with a random variable, which is what we called as the entropy. And we tied together that with the notion of KL divergence, which is basically the divergence or sort of the separation between two distributions, right? Okay, so now where does the cross entropy loss comes into play? Now, when you have a data set, right? So let's take this example scenario where you have sample I. So this is sample I. This may correspond to, for example, 5 features. So the 5 features could be heart rate, blood pressure, temperature, sugar level, and the vitamin D levels, right? Now this patient has a label Y of I. This is the label for that patient. And let's say this could correspond to 3 possible values. This would correspond to 3 possible categories. Just like the example we saw in the class, the categories could be diabetic, non-diabetic, and pre-diabetic. Non-diabetic and pre-diabetic. So what do we have? So here there is a particular probability given that I have patient X of I, the label corresponding to the patient is one of those 3 categories. This is the true probability for patient I. True probability for sample I. Given that I have all those 5 features, for example, heart rate is 74, blood pressure is 128, and so on, what's the probability that this patient belongs to the label Y of I? This is the true probability for sample I. What does a machine learning model do? For example, like a softmax or a neural network model do? It has a probability that it's predicting, right? So I'll call it P star, right? It's predicting what's the probability that the patient belongs to the label Y of I, given that they are X of I, right? And then the model generally uses some weights and biases, right? So I'll just put it as just W, representing all the model parameters. So this represents all model parameters. So using those model parameters, given that I have patient or sample Xi, it tells me what's the probability that the patient belongs to the correct label Y of I. This is the predicted probability that the sample I belongs to its correct label, right? The first one is a true probability for sample I belonging to their correct label. The second one is the predicted probability for sample I belonging to their correct label. So you see there are two distributions, right? So for example, let's say that patient Y of I is diabetic, right? So what is the true distribution? So the true distribution we know is one hot encoded, right? So the true distribution would be, so we always write the information corresponding to a sample as a vector, right? The true distribution is diabetic has probability 1, non-diabetic is probability 0, pre-diabetic is probability 0, right? So, but then the model would predict a distribution. Model predicts the distribution as follows. Model predicts this distribution. Let's say it has the probability of 0.3 for being diabetic, 0.5 for non-diabetic, and 0.2 for pre-diabetic, right? So this is like our, so let's recap the KL divergence, right? So here you have your Q. This is like your friends distribution. This is your original distribution, and you want to calculate the KL divergence between these two distributions. What's the KL divergence between these two distributions? That's the same as saying the KL divergence between your correct distribution P and what the model tells you, which is P star, right? So we're going to make use of the definition here, right? So here, if I use that definition, you have the cross entropy between P and P star. So the sum over all possible. Now it's not over X, but it's over Y, right? So because Y corresponds to the labels, it's the sum over all possible values of Y, because P and P star are distributions for Y, right? The sum over all possible values of Y, I have P of Y log P star of Y, and then you have plus the sum over all possible values of Y, P of Y log P of Y, right? Now, what we want to do is we want to find a P star. The goal is find P star such that the KL divergence between P and P star, which tells how different is the model's distribution from the true distribution, right? Find P star such that KL divergence between P and P star is minimized, is as small as possible, right? So if you want to do that and you look at what the KL divergence on top is, the second term, this term here, has nothing to do with P star, right? There is no P star there. This term has nothing to do with P star. This is the entropy of the random variable capital Y, right? So this is something you cannot control. The only term that has P star is the first term. This is the only one that has P star. In other words, we want to find a distribution P star such that that term is minimized. So minimizing the KL divergence between P and P star is equivalent to minimizing the cross entropy between P and P star, right? So minimize the KL divergence between P and P star is equivalent to find P star, the distribution that your model gives, such that the cross entropy, which is over Y, sum over Y, P of Y log P star of Y is minimized, right? And this precisely is the reason why it's called the cross entropy loss. So what will be the cross entropy loss for this example? Well, what are the possible values of Y? Diabetic, pre-diabetic, and non-diabetic, right? So in our example, so I'll just copy this example again. So let me just copy this again. Okay, so here it is. Let's copy this. And paste it here. Okay, in this example, what is the loss, the categorical cross-entropy loss? We know that the categorical cross-entropy loss is exactly this quantity, right? There is the cross-entropy term, and we want to minimize that, right? So the CCE loss is simply the CCE loss is simply the sum over all possible values y. You have your true distribution for y, there's a negative sign, times the log of what the model gives you as the distribution for y, right? So y is diabetic, pre-diabetic, non-diabetic, right? So in this case, probability that the person is diabetic is 1, so it's a minus sign, times log of the probability that the model tells you the person is diabetic is 0.3, plus probability that the person is non-diabetic is 0, probability that the model tells you that the person is non-diabetic is 0.5, plus probability the person originally is pre-diabetic is 0, times the logarithm of the probability that the model tells you the person is pre-diabetic is 0.2, log of 0.2. So if you simplify all that, you see that this is equal to the negative log of 0.3, which is the negative log of the predicted probability that the sample belongs to its correct label. And that is how we started, right, our discussion. In fact, that is how we have motivated what cross-entropy, categorical cross-entropy loss is, and that is how we also started today. So if you go all the way up, so this is how we started. The cross-entropy loss, right? So I'll write it as cross-entropy here. Cross-entropy loss is the negative log of the predicted probability that the sample belongs to its correct class. So when we are saying we are minimizing the categorical cross-entropy loss, what we are actually doing is we are minimizing the KL divergence. How different is the true distribution of the output label from the distribution, which is basically the probabilities, right, that the model gives us, the difference between P and P star. And that basically has this term, the cross-entropy term. So minimizing the KL divergence between the true distribution and the model's distribution for the output label is the same as minimizing the cross-entropy between the true distribution and the model's distribution for the output label. And that is why it's called the categorical cross-entropy loss, right? Okay, that is it.